Welcome back, guys. So today we'll be diving into the fascinating world of sub-gigahertz frequencies. This can be seen as the invisible highway of data transfer that, for the most part, is unseen or untapped. Before we dive in, don't forget to hit the subscribe button and bell icons so you never miss out. It's a long one, so buckle up, turn up those speakers, and let's go. So when we think about it, wireless technology lets our devices communicate without the need of physical connections, and these operate over various frequencies. The sub-gigahertz frequency, which, as the name suggests, refers to frequencies below 1 gigahertz, is especially important for long-range, low-powered application. These low frequencies have better penetration capability, making them ideal for situations where signals need to pass through objects and obstacles. The use of sub-gigahertz frequencies in communication technology goes back to the beginning of radio technology. While it's difficult to attribute the development of this specific technology to a specific inventor, there are certainly some key figures and milestones in history of radio waves and wireless communication that has led to the development of modern sub-gigahertz technology and the Flipper Zero that we will later review. Brief history. James Clerk Maxwell and Heinrich Hertz. The theoretical foundation of radio waves was laid by James Clerk Maxwell in the 19th century, and the existence of these waves, at least an experimental level, was confirmed by Heinrich Hertz, Tesla and Marconi. Now this one's a story close to my heart, but both were credited as the fathers of long-distance radio transmission, although it was much later that the patent was stolen from Tesla, as you learn in history. And this was achieved in the late tail end of the 19th century, early 20th century. Both men's works have been foundational to the development of radio technology, including those that are still used today in the sub-gigahertz spectrum. Fessenden and Lee DeForest. Fessenden made the first AM radio broadcast on Christmas Eve of 1906, and Lee DeForest then invented Audion, a vacuum tune device that could amplify weak radio signals, a key invention for all radio communication. Edwin H. Armstrong, he invented the FM radio in the early 1930s. Now, FM radio signals are less susceptible to noise and interference than AM signals, proving clearer sound quality and modulation. Modern digital technologies. First, we have the 1G cellular network. These were introduced in the 1980s by multiple companies around the world, making the first use of the sub-gigahertz frequencies from a cellular communication perspective. Notable companies involved in early cellular network include Bell Labs, Nippon Telegraph and Telephone, or NTT, and the Nordic Mobile Telephone, the NMT. Next, we have 2G cellular networks, or GSM. So the global system for mobile communication was developed in the 1980s and commercialized in the 1990s, introduced digital encryption and data services like SMS, for example, for mobile communication. Next, we have Zigbee. Zigbee Alliance, now Connectivity Standard Alliance, introduced Zigbee in the early 2000s. Now this standard supports sub-gigahertz frequencies from that 868 to 915 megahertz. Along with some work in the 2.4 gigahertz frequency range, and are widely used in smartphones and smart home technologies today. Z-Waves, or Zen Systems, is a Danish company which introduced the Z-Wave in the early 2000s. Now this operates around the 900 megahertz range and is also commonly used in home automation technology. Next, we have LoRaWAN, developed by the LoRaWAN Alliance. LoRaWAN is a low-powered, low-range communication protocol designed for the Internet of Things applications. It operates on various sub-gigahertz bands depending on the region, which is around the 868, 915, depending whether you're in North America or Europe. Sigfox. Now, this was founded in 2009. Sigfox is a French company providing global low-powered wide-range area, or LPWAN, services for Internet of Things applications, and this also uses sub-gigahertz ISM bands. Wi-Fi Halo, or Halo, under the 802.11ah banner, So this introduced by the Wi-Fi Alliance. Wi-Fi Halo operates in a frequency band below just under 1 gigahertz, providing longer range, low-powered Wi-Fi solutions compared to traditional Wi-Fi. Lastly, we have NB Internet of Things, or Narrowband IoT, which is a standard introduced by 3GPP of Internet of Things applications over cellular networks once again. So this is utilizing sub-gigahertz bands for long-range, low-powered communications. Now, going through all of this, you can see a lot of the sub-gigahertz band is already a space stack occupied and purchased. So all of these sub-gigahertz channels are channels that are privately owned, militarily or governmentally owned, or used in some other reference. So there's not much wriggle room for non-commercial use, and that's where the illegal activity can occur if you're overstepping the mark in terms of transmitting or receiving on these frequencies. That's why I thought it was quite important to break down how long this has been going on. Now, while specific key inventors may not be named for these technologies, I did name the companies but not the people behind the tech. These milestones show the evolution and application of sub-gigahertz technology over time. Flipper Zero. Now we have the Flipper Zero, which we know is a powerful tool that can receive and transmit radio frequencies ranging from the 300 just under the 1 gigahertz range, which is the 928 megahertz. Now, this is capable of reading, saving, emulating remote controls used for gates, barriers, radio clocks, and much more. But how does it all work? Let's find out. Flipper Zero hardware. Now, at the heart of the Flipper Zero is built in the sub 1 gigahertz module based on the CC1101 chip and the radio antenna. This hardware allows Flipper Zero to operate at frequencies, as mentioned before, which is 300 to 928 megahertz bands. Now, this chip, first developed by Texas Instruments, is a chip essentially to bridge between the digital data in the device and the analog radio waves used for wireless communication. Now, it converts outgoing digital data into modulated radio signals and incoming radio signals into demodulated digital data. Now, if you're looking for a radio chip that provides more features and greater flexibility, having tested this already, I would recommend the Semtech SX1276. Now, whether this can be adapted into a Flipper Zero is another question, but this is definitely a better chip than the CC11. Now, the sub-gigahertz menu is your command center, so let's take a look at it. Now, from here, you can read, emulate remote controls, add controls manually, and even determine a remote's frequency. Reading signals with the Flipper Zero. So, reading signals with the Flipper Zero is pretty straightforward. You have a read function here, where it can scan depending on a frequency that you dictate. Now, the read function operates on a pre-configured frequency and modulation scheme, which you can see here is set as 433.92 AM by default. Upon detecting any activity on the selected frequency, it outputs a relevant data on the screen, which can subsequently be used for signal replication or modification in the future. Now, while the read operation is ongoing, you have an option to press the left button to access configuration, as you can see here. Now, currently the device supports 4 modulation types. It has an AM27, you can see here, a 650 or a 328 on an FM band, and a 476 on an FM band. So those are the 4 modulation types. And a host of important frequencies are stored within the system itself, which we will later look at. Now, you're at liberty to select any frequency that aligns with your requirements. However, if the exact frequency employed by the remote device has an unknown origin or band, you can enable what's called the hopping function, which is here. Now, this is set off by default. Now, what the hopping function does is trigger an action button several times until the Flipper device intercepts a signal and provides you with the necessary information to set the correct frequency. So if we were to enable this, you can see here the frequency goes off. Now, if we go back now and you're scanning here, you can see here it's hopping through various channels And then you can obviously dictate the hopping range, as it were. So if you're unsure of a device that you're trying to scan for, but you know a range it might be in, the hopping frequency feature might be quite convenient for you to use. So let's just take that off for now. Put the AM60 back in place. And there we have it. Now, transitioning between frequencies can result in a time lag, which could potentially result in a loss of signal transmission during that switchover. So for an enhanced signal reception, I would recommend to set a fixed frequency, which can be ascertained using the frequency analyzer tool, which would be here. Now, in terms of signal transmission, it's quite easy just to send a signal as well as read or write a signal. Now, sending a save signal is just as easy. You can go to the sub-gigahertz menu and select save. Now, from here, you can select various repos. I would recommend Ubers, of course, and you can obtain many sub-gigahertz frequencies as and when you need them. Now, for example, we can select doorbell here, and there's a various cluster of doorbell types and brands that you can select here. And literally, once you find the right one, you have this sub file here. Now, if you hit enter on here, you have a few options available to you now. So you have the raw version of that file that was collected. And usually once you send these, they transmit for 30 seconds. If someone knows how to transmit these for longer, please let me know in the comments below. But once you hit send, you can see here, it's transmitting that frequency out. You do have a more option, which is to rename and delete it. Or you can do a new option, which is to record a different frequency, reading raw signal. Now, Clipper0 can also record signals in raw format. This is particularly useful for signals with known or unknown protocols. The read raw function captures signals transmitted on a selected frequency, allowing the potential for signal interception and replication. Now, by default, read raw is also configured at that default band of 433.92 on the AM, as you can see here. However, if the read function has identified a signal of interest on a different frequency or modulation, these parameters can be adjusted. This adjustment can be made by pressing the left button while inside read raw option. So, as mentioned before, we go back into config and you can change modulation and frequency right here. The first example I want to show you is just reading and recording a raw sub frequency. Now, for example, here I have a doorbell in front of me with a receiver. Now, once we hit record, you can see here the RSSI is recording and it's intercepting signals as and when it needs to. Now, until a signal of interest pops up, you will see a spike. Now, as you saw there, there's a significant spike in the frequency analyzer. That was the doorbell going off while there's more noise still occurring in the background. Now, I'll stop recording. Now, you can change this in terms of you want it just right in terms of the threshold. So the threshold, we can lower it or increase it as we need. So if we increase it once more and we go back, and now you can see the threshold's lower, so it's not picking up anything but the frequency I'm interested in. And we hit record again. Now you see here the threshold was reached and it goes back out. Now this is particularly helpful when you just want a crisp recording of a set frequency and not additional noise. It comes helpful when it comes to post-analysis of the frequency on other software we can use later. Sending raw signal. Now, in terms of sending raw signals, we want to save, for example, the signal that was intercepted. And then we can just call this anything we need to. Just call it test for now. I'm not going to have much test on here anyway. So now test is being saved. What we can do is send test. Now, sending raw signals is similar to sending regular signals. You simply select the raw signal from the save menu and you press send, and we send it. Now, as you can see, we collected that crisp frequency from the previous capture, and we was able to send to the doorbell. Supported sub-gigahertz vendors. FlipperZero is compatible with a wide range of vendors. If your remote or receiver isn't supported, you can contribute it to the Flipper community on GitHub or other channels, and sharing information about various remotes out there. Now, on the screen, you can see a list of frequency bands and regions, and as you can see here, it is massive. Now, to find out what frequency your remote control works on, you can use the frequency analyzer like we looked at, and this tool can scan for signal strength at all available frequencies and display the frequency with the highest received signal strength indicator, which is the RSSI. Now, the caveat within this, and it's built in within the official firmware, is that sometimes you will get a transmission blocked error on the Flipper device itself. Transmissions on certain frequencies, like I mentioned earlier, are restricted to a specific region. Now, if you try to send recorded signals at frequencies that are prohibited for civilian channels in your region, the Flipper is going to let you know about it. It's always important to be aware of these restrictions and why they're there. Now, that's not to say within certain custom firmwares like Unleashed or Extreme, you can lift these restrictions or tweak them using your own settings, which I can demonstrate later. But remember what I said earlier, those restrictions are there for a reason. Frequency examination. Now, if we go into the official firmware and we look under the hood a little bit, there are 3 particular files of interest that I want you to explore even. Now, the first file of interest I want you to examine and poke and prod around on is the Furry Howl folder under F7. Now, we go into this file and you can see here there are a few things available to us. The first thing is the country code or region that we want to set. Now, you can set this as whichever region is applicable to you. Like, for example, here we got EU, you got the band count, you got the start and end frequency ranges, power limits, and duty cycles. And the same goes for the US. It's got certain frequencies, Japan, etc. You can add your own and edit this code as you want, really. It's important to know where it exists so you can play around with it and set your own frequency bands and have a go. The next file we want to look at is the sub-gigahertz setting file. Now, this file is of particular interest because here we can set our read and raw frequencies and also set the hopper frequencies. So as you can see here, they sets the different regions and the frequencies that are static within those regions. And also we can set the hopper frequency here as well. Now, if we take, for example, the FlipperZero itself, and we go into read config, and then we can look at these frequencies. For example, the 43392, that would be down here. 43392 down here, and we keep going. All of that correlates to what's happening right here. We got the 868 down here, etc. You can see here, here's the hopper frequency list within that region. So this is where this can be edited and manipulated if you need it to be. The last file of interest is the settings user file. Now, this file dictates the standardized settings for the frequencies that are being used, and in most instances the standard is set to true. Now, this standard being set to true, it will use whatever default presets are already within the Flipper in this frequency and modulation range. Now, if you were to set this to false, you would have to remove the hash first in order to activate this line of code, and you would type false, of course. Now, once we set this to false, it says here to rename it just to users. So it would be just settings underscore users. If we really wanted to make this live, for example, it would look like that. And then here, you can see here, the frequencies used for read raw frequency analyzer. So here's the frequencies. If we wanted to, that is, we can literally just type a frequency that we want to see on the flipper and then unhash these to also see those frequencies again. You can also set your hopping frequency ranges here. So these are the frequencies used for the hopping mode, and then you can set them here. And then you can add a custom preset. For example, you got AM1, AM2. You could just literally copy this and then put your own preset in. You save that, add that to the flipper, restart it, and then these should show up. Experiment 1. So as I mentioned, we kicked off things by acquiring a doorbell that sends out a sub-gigahertz signal when clicked. The first order of business was to identify the frequency of said bell. Now, we mentioned already that we could use the analyzer here, which I didn't like too much. But for me, it's either the read raw, which we could set the ISR value, which is more specific, or we can use the frequency analyzer. Now, both work very well. My preference here would be the read raw. Now, the read range for the Flipper Zero is quite a crucial factor here in terms of feasibility of intercepting sub-gigahertz signals. Now, if the signal was just, say, a foot away, for instance, it drastically decreases the chance of covertly catching a signal from said doorbell, a fob, or a similar device. However, the Flipper Zero proved to be surprisingly good in terms of range. And don't forget, because this is a modular device, we can actually amplify the signal. Leave a link in the description below if you wish to do that. Now, I was able to capture the sub-gigahertz signal from, say, 20 feet away if I press the bell, but you would see from the RSI, the signal strength is quite weaker. So to maximize the effectiveness of the range, I would suggest amplifying it using a third-party modular device or using a different device if it's quite a distance away. So let's put this to the test right now. So if we record this, all right, that's me being right next to the Flipper Zero. So I'm going to step away from, I'll leave the receiver next to the flipper, but I'll take the doorbell with me and see how that looks. Now that didn't pick up anything right now, so what I'll do, I'll edit. I'll stop recording, erase that, and I'll configure the RSI. The RSI ain't on at all, so if we start recording, now you can see I'm right next to the device again. I'm going to step away from the computer and take the remote with me. Now, as you saw, the further I got away from the receiver and the remote, the weaker the signal became. But nonetheless, the signal was still captured in some respect. What I did note, even just recording from the analyzer, was the fact you couldn't track back or move backwards while the screen is constantly recording. So that'd be a very nice feature if there's any clever dev that can resolve that. Now, as I mentioned, sub-gigahertz are renowned for its longer range and low-powered consumptions than Wi-Fi or Bluetooth protocols, for example. Now, this makes it particularly well-suited for Internet of Things applications. Now, sub-gigahertz networking can easily reach several hundred meters indoors and, in certain conditions, several kilometers outdoors. in a military perspective at least. Now, a more holistic approach to a potential attack brings us back to the conversation about frequency. Now, this hurdle can easily be overcome by creating a module or custom script to adjust the frequency hopping behavior. By programming the hopping to stay on a specific frequency for an hour and save the captured signal and then rotate the next frequency, I could feasibly capture the signal that I needed. Now, leaving the flipper near a target reader, for example, overnight or even several days, then returning later to retrieve it, might seem like a good strategy, but in real world, someone's just going to teeth that. You're going to lose your flipper and you're going to be none the wiser even if it worked. So obviously you'll have to conceal it if that was the case in a smart way, covert way, and then come back to the recording once it captured it. Or you need a specific device that can just capture signals rather than an all-in-one like Flipper is. Now, the Flipper Zero frequency analyzer tool, like I said, I find it a convenient option to run while you're near a target reader. However, it's worth noting that depending on the location, there might be an abundant amount of signals varying different strengths, which could make it more difficult to discern which signal is related to said target device. I kind of overcome that when I showed you that you could bring down the threshold for the RSSI, but in a noisy environment, that might be an issue. If a physical security pen tester cannot get close to otherwise observe the target device tag, an online search might be a good alternative. Thorough browsing on eBay or other e-commerce sites, a manufacturer's website, should help you pinpoint a relevant model for a target device and finding its FSID or FCC ID number. Lastly, for me, what might be a notable point here is the ability for Flipper to also not only read and send signals, but also block signals. So as mentioned, if we got the RSI value up here, and for example, let's just analyze the signal. We don't want to record it. So if we got this signal and we're analyzing, now you can see the doorbell first rang at the 899 range on the 433. Again, we have another signal, and let's do it one more time. Now here we've collected 3 rows of different signal bands. Now we can see from here we are operating in that 899-9119 region. Now if I was to transmit a signal at the same frequency, the bell wouldn't ring when I clicked the receiver. Now then, if I go into my application set under sub gigahertz and I go into my jamming signals and we run the jam under the 43392 and we run this application first and then try doorbell. Oh, still working, it didn't jam nothing. So let's try to put this in between these two. There we have it. What was funny, I literally put this I put the Flipper device in the middle of what's happening on the screen, and that worked just fine. Now that's jamming the signal. No signals getting through the doorbell. If I stop sending on that works just fine. Now, if you're interested in jamming frequencies and creating them, you can either create them yourself or you can head over to Shuriken, who's done a decent job of compiling a few different frequency ranges, and he has an open GitHub repo on a few jamming frequencies, which is a demo of the one I just used just now. So in conclusion, on the first experiment, aside from the potential logistical issue of determining the relevant frequency and how it might be viable to capture a range. Placing or using the FlipperZero near a gate or doorbell device or other sub-gigahertz device, it might be a viable means of gaining access to that target. Despite the technical hurdles, potential for a higher success rate is there. Tesla port. Now, another area of fun and sub-gigahertz territory is the Tesla charging port. Now, this uses the remote control that operates on the 31 megahertz range, which falls within the frequency range of the FlipperZero, which can interact with it. Now, by no means am I condoning it, and it's fully illegal, but let's say, for argument's sake, how does one interact with this? So when the FlipperZero is set to the same frequency as the charger port, which is the 315 megahertz, it could potentially read the signals sent by the remote and send them out. This means it could replicate the signal to interact with the charger port. But there's an important note of caution here. It's illegal and unethical to use this kind of technology to manipulate devices without permission. Again, this video is purely for educational purposes, showcasing technology and how it has potential applications. Other use cases. Now, there are a few use cases in terms of how the device can help one within either a legitimate profession or within the ethical hacking perspective. Now, in the context of cybersecurity and hacking, sub-gigahertz frequencies are of interest for a few reasons. Now, you have device communication. Many devices communicate over these frequencies, often without strong security measures in place. This can make them vulnerable to various types of attacks and inspection and audits, and help your clients. Signal interception and analysis. With the right equipment, a hacker can intercept and analyze signals transmitted over sub-gigahertz frequencies. This can potentially reveal sensitive information such as the data being transmitted between devices. Replay attacks. Now, if a device uses a static code to authenticate wireless commands, an attacker could capture this code and replay it to perform an unauthorized action. This is a common vulnerability in older garage door openers, remote keyless entry systems, and very older modeled cars. For instance, in the context of rolling code system, only read raw is capable of capturing the sequence of changing codes, while the read function may not be able to interpret this data effectively. Device jamming. Now, we sort of demoed this, but an attacker could potentially jam a sub-gigahertz frequency used by a device, preventing it from communicating or receiving incoming signals. This could be used to disable a security system, for example. Device spoofing. If an attacker could understand the communication protocol used by a device, they could potentially spoof the device, sending false information or commands. Lastly, we have brute force. Now, if you know the protocol used, for example, by a garage door, it's possible to generate all the codes and send them with the FlipperZero device until you literally brute force your way into said door. Conclusion. Now, I hope you enjoyed that one. It was quite a thorough session, but in the realm of ethical hacking and pen testing, understanding and being able to exploit vulnerabilities in the sub-gigahertz communications can be a valuable skill set. It allows security professionals to identify and address vulnerabilities, improving security systems for their customers and clients. Now, the FlipperZero is a device that can be used to interact with sub-gigahertz frequencies, making it a valuable tool for cybersecurity professionals. It can receive and transmit signals in the sub-gigahertz range, allowing it to read, save, emulate remote controls. Now, this can be used to test the security of systems that can communicate over these frequencies and help you identify any vulnerabilities. Now remember, your contribution to the FC community can make a big difference. Thanks for watching, stay safe in the cyberspace, and peace out.